So, kernel matrix. Right, so here's the idea. We take the perceptron. So this is actually the traditional way that people derive support vector machines is they start with the perceptron and they say, let us replace the dot product by a general kernel. Okay? And then we have something much more powerful. And in particular, so why is it more powerful, right? And how can we understand what's going on? This is also a very interesting part of this, right? Well, the key objects to think about is what's called the kernel matrix. Everything in support vector machines revolves around the kernel matrix. The kernel matrix is just a matrix of n by n. If I have n data points, the matrix is a square matrix of n by n, and the ijth entry is the similarity between the ith and the jth training example. Okay? So k of x prime is the value of the similarity assumed non-negative between x and x prime. Okay? Right, so this is my kernel matrix. And if you can do things efficiently with kernel matrices, you can learn support vector machines efficiently. Unfortunately, you already see one source of inefficiency for support vector machines is that when your training set is large, this thing is going to be quadratically large. So, scaling out support vector machines is its own interesting problem that we won't get into here, but there's actually, some good solutions to it. However, at the end of the day, support vector machines are not the most scalable machine learning algorithm around. But if you have the cycles to apply them, and and your training set is compatible, then support vector machines might be a very good thing to use. So let me now, remember I said, well, there's all this kernel theory underlying what we're going to do here. Here's where we're going to use something from kernel theory. But I'm just going to say it and hope that you believe me. And it involves a little bit of jargon. But hey, that's life. So let me make the claim first, and then let's see what it means, right? And what it means is actually very interesting. Let's suppose that I have a kernel matrix that is symmetric, right? So I'm assuming that it's symmetric, right? So kxx prime is equal to kx prime x, right? Well, for a similarity function, this makes sense, right? Let's suppose that this matrix is positive semi-definite, right? This is actually something from linear algebra. This means that the matrix has non-negative eigenvalues. If you don't remember your linear algebra, just forget I said that. If you remember your linear algebra, you can go like, okay, I know what you mean, right? But either way, then this is the thing that's like not obvious at all, but very important. My kernel matrix, you can think of the kernel, like the kernel is something that is defined over all space, right? And you can use it in doing integrals and whatnot. But a matrix is just sort of like a finite instantiation of the kernel, right? It's just the similarity for this particular set of data points, right? This is still a dot product. This interesting thing is that we started out with our good old friend the dot product, and then we replaced it by a kernel, made things much more powerful, but we can still squint at that kernel and say, you're still a dot product. You're just a dot product in a different space. The reason this is important is that linear algebra is easy. If we can do everything with matrix multiplications and dot products, life is good. Right? I mean, again, it doesn't scale ideally, but it's very simple. Much simpler than things like multi-layer perceptrons and whatnot, right? That are really hard to, understand what's going on when you're learning it. So the claim that I'm making is that any kernel, right, with these properties can be expressed as follows. As the dot product, so the kernel between x and x prime can be expressed as the dot product of phi of x and phi of x prime, where phi is a transformation that takes your original features, let's say your d features that you were using to describe your examples, and computes a new set of features from those. That could be fewer or more. They could even be infinite. I could be computing an infinite number of new features. This is one of the things that gets some people really sort of like, enamored of support vector machines, is that this is all happening in infinite spaces, also known as Hilbert spaces. In fact, that doesn't really make too much difference to our daily life, but the interesting thing is that support vector machines are going to effectively be doing dot products in infinite spaces in finite time. Okay? So I've just made this claim so far, but I'm not going to prove it in general, but we will see, an example of how this comes about, right? But nevertheless, right, the importance of this is twofold. One is that I've gained all this power, but I'm still in familiar land, right? I'm still doing only linear algebra types of things. This is one very big gain, right? The other very big gain is in this formulation, and one thing follows from the other, I still have a convex weight optimization problem. When support vector machines came along, the main thing that they competed with, and in many cases displaced, was backprop. The thing about backprop is that, well, it's an optimization problem with lots of local optima. You have to fight with it to make it work, and you'll get one result, I'll get another result. With support vector machines, that all goes away. It's a single global optimum. As long as we both got the same problem statement, we will get the same result. So this is, and we don't have to worry about getting stuck in local optima. Our optimization is now much simpler. Of course, there's no free lunch, and we will see where where you're paying the price for this. But nevertheless, in many ways, compared to something like backprop, this is a great gain. Okay? Questions about any of this? Now, here's something to just, a side note that's not going to be important to the rest of the class, but is worth bearing in mind, is that the kernel trick does not just apply to SVMs. People started out doing it in SVMs, but then they went, hog wild, and they started applying the kernel everywhere. The way you can apply kernels everywhere is by saying let me look at my machine learning algorithm that was using a dot product somewhere. I'm going to take that dot product, I'm going to replace it by a kernel, and I'm going to say, you're still a dot product, just in a high dimensional space. So I think pretty much these days, any machine learning algorithm that uses dot products has been kernelized, as the lingo goes. Okay? So this idea was important not just because it led to a better classifier support vector machines, but it's been applied in many other areas. Like for example, next week we will talk about dimensionality reduction. You can use the kernel trick to do nonlinear dimensionality reduction. Okay? So this is a very powerful thing to have. Okay? All right. So let's see an example of kernels, and then we'll take a break. Okay? So I've just made this claim to you that sounds, very appealing, right? But why should you believe it? Okay? Well, let's see, number one, what some of the kernels are that you might want to use, and number two, how things actually work out concretely. Okay? And by the way, when you see people, in say one lab, I actually know examples of this. Like there's some problem that the company needs to solve, right? And there's the neural network aficionados and there's the support vector machine aficionados, and they're competing to see who comes up with the best solution, right? What they're doing, right, is they're doing different things. The neural network people are playing with the kinds of parameters and choices that we saw when we talked about neural networks. The number one thing that the support vector machine people are likely to be playing with is the kernel. They're going to be trying different kernels. And this shouldn't surprise us because, after all, SVMs are instance-based learning, and we saw that the key thing, in instance-based learning, the place where you put all your, understanding of the problem and knowledge and whatnot is in the choice of similarity function, which in SVM lingo is the kernel. Okay? Nevertheless, so in practice, when you use SVMs, choice of kernel is one of the main considerations, and people these days, people have come up with amazingly clever and sophisticated kernels. You can have kernels to compare graphs. You can have kernels to compare strings and do NLP with them, right? You can have kernels to compare any object in the world. Okay? But, having said that, just as in, nearest neighbor, Euclidean and, Hamming distance, or value difference metric got you, pretty far in many applications, there's a few standard kernels that, people use all over the place. And, they're probably what you want to start with. And the three most popular ones are linear kernel. Linear kernel is just another way of saying don't do anything. Just use our good old friend, the dot product. And you're like, well, really? You just kind of poured scorn on that and said it's not very powerful, so why bother, right? Well, here's why. Support vector machines, were a theoretical notion, and then they took off when they had successes in three important areas that we've already met. One is comp bio, another one is digit recognition, and another one is text classification. And in a way, text classification is the most revealing one because that's actually where the biggest gain happened. Suddenly you're doing much better text classification. And previous to support vector machines, kind of the best algorithm, to people's surprise, was naive Bayes. Right? And we saw why naive Bayes might do well at text classification, but here's the thing, is that in text classification, the dimensionality of the space is so high, right? I could be using 10,000 words as my features, or even just 1,000. I mean, even 1,000 is a huge dimension, right? That even naive Bayes starts to overfit. How can naive Bayes that's just a hyperplane or a perceptron overfit, right? Suppose that one of my words, just by coincidence, correlates very well with the class, right? It's just, a random event in the training set. If I'm giving myself 10,000 words, and I don't have a lot of examples, let's say, to exert things a little bit, that I have only 100 examples, right? The chances are not bad that, some one word will always, appear in documents of class, interesting, and not appear in documents of class boring. Right? So even if the dimensionality is sufficiently high, even naive Bayes is prone to overfitting. And support vector machines avoid that overfitting, and that's why they do better than naive Bayes. Okay? And we will see how support vector machines avoid overfitting. So the moral of the story is, even just the dot product SVM can be a very good thing to use if you're in very high dimension. And these days, big data, etc., high dimension is very common. Okay? So linear SVMs are widely used, and in particular for things like, say, text applications. Okay, but that's not very interesting. Let's look at a slightly more interesting one, and this is the polynomial kernel. Okay? The polynomial kernel is a very simple idea. I just take my dot product and I raise it to a power. Okay? Now, just taking the dot product and raising it to a power doesn't give me a complete full polynomial of that degree. In general, you might want to use that, polynomial of any degree. But for our purposes, this is easier, and for many applications, it's enough. Okay, so a polynomial in general is literally any polynomial, but in particular, it can just be the dot product raised to some power. Okay, so very innocent thing that we did, but as we'll see, just by raising the dot product to some power d, which by the way is not the dimensionality of the data, it could just be 2, for example, is suddenly going to give us a lot of power that we didn't have before. Okay, and finally, what perhaps is the most widely used type of kernel is, again, a good old friend of ours, the Gaussian. Right, remember radial basis function networks? Right, we saw that radial basis function networks are both a kind of neural network and a kind of instance-based learning. Well, the SVM analog of radial basis function networks is Gaussian kernels. And for a lot of things, SVMs with Gaussian kernels are a better thing to use than radial basis function networks. RBF networks can be trained in a whole variety of ways, some of which for some problems are better than SVMs. But nevertheless, if I had to tell you which one should you try first, RBFs or Gaussian SVMs, I would say, well, this is Gaussian SVMs. They're easy to train and they'll probably do quite well. Right? In a way, a Gaussian is a very natural, similarity function to use, right? It just says, well, you're maximally similar if you're at the same place, and you have this nice bell-shaped, degradation of similarity as the two examples become more and more different, right? So what exactly is the Gaussian kernel? It's just the exponentiated norm, or Euclidean distance squared between the two examples, okay, divided by sigma, which is your kernel width. Okay, and this, guess what, is a parameter that you have to set by cross validation, and will make a lot of difference to whether you overfit or not, or underfit. Okay, so if sigma is very small, right, that means that even a small difference in your examples means the similarity is going to be very low, right? It means that your Gaussian is very narrow, right? A high value of the variance, right, means that you're allowed to vary a lot, means that the similarity decays only slowly with Euclidean distance, right? So you take Euclidean distance, you put it through this exponential, and you get the Gaussian kernel, okay? The Gaussian kernel is also cool because in this case, you are in infinite dimensions, right? Remember, this is actually a very strange statement to think about. Like, really, you're saying that this thing is equivalent to just doing some dot product of some features? Really? This is not obvious at all. Well, it is, but it's of an infinite number of features. Okay, and there's a fairly straightforward proof of that, but we're not going to worry about that here. Let us look at the simplest interesting case, which is polynomial kernels. Any questions so far? Okay, so let's look at, in particular at the simplest polynomial kernel, which is just the dot product squared. Okay, let's see how that works. And let's, as an example, right, this is going to illustrate why it is the case that a kernel can still be seen as just a dot product in a different feature space, and what power that gives us. So let's suppose that I have two vectors. These are, two examples, right? One of them is u1, u2, and the other one is v1, v2, right? So these are just on the plane, right? Low dimensional, right? This is just a toy example, but it'll illustrate something important, right? So my example u is u1, u2, right? And my example v is v1, v2, okay? Well, now let's compute the kernel, over these two, right? It's going to be u dot product v squared, okay? So u dot product v is just u1, v1 plus u2, v2. You agree? Right? That's the definition of dot product. And now I square this, right? This is where my new extra power comes from. So what is this squared? Well, I get, u1 squared, v1 squared, plus u2 squared, v2 squared, plus 2u1, v1, u2, v2. Okay? Right? If you take this squared, you get this, so on and so forth, right? So this is just expanding the square. Okay? So now, this is the key step. It's going from here to here, right? So what is a dot product, right? It's a sum of products of corresponding terms, right? That's what a dot product is. So if we want to show that this is still a dot product of something, we have to reduce it to that form. Okay? Well, so let's do that, right? Well, I still have a sum of three things here, right? And the key thing is that I have to be able to split each of these things into a part that depends only on u, or a coordinate of u, right? Times a part that depends only on the corresponding coordinate of v, right? So let's do that, right? Well, this guy here obviously is just a product of u1 squared and v1 squared, right? So the first component of my vector, right, is going to be u1 squared, right? And now here it's just the same thing for u2 and v2, right? So what I'm doing here is constructing my new feature representation of u and v, right? And so far all I've said is I'm going to replace u1 by u1 squared and u2 by u2 squared, right? I'm just squaring the coordinates. Nothing exciting happening here so far, right? I haven't gained any power with that, okay? But now comes the trick here and interesting part, right? What about this term, right? 2u1, v1, u2, v2, right? I can still squint at this and see here a product of two things, one of which has only to do with u and one of which has only to do with v, right? Namely, square root of 2 times u1, u2, right? Notice, I have here u1, u2, right? Those go to u, right? Go to the, feature vectors for u. Same thing for v, right? And now I have 2, right? But I need to split the 2 into things that are the same in both vectors, right? Well, that would be square root of 2, right? Because I'm going to multiply them, okay? So basically what I've shown here is that I can express this as a dot product of the following vectors. u1 squared, u2 squared, square root of 2u1, u2, and the same thing for v. Okay? And you can certify yourself by doing the dot product of these two things, right? Well, this times this gives that, and so on and so forth. Okay? So, if I just call this guy phi of u, right? And the same thing for v, I've just shown that, u dot product v squared is really just a dot product of two different feature vectors for u and v. And you just need a recipe to compute the new feature vector from the old one. Now in practice in SVM algorithms, we're not going to bother to do that, right? Because, as I said, the feature vector might even be infinite in length, right? But the main point is that we know that this equivalence is there. So I can still apply to this all the math that I apply to dot products. Okay? And now you might ask yourself, okay, well, this is all very interesting, but what did I gain with this? And here's the amazing thing is that I've gained a huge amount. Because with u dot product v, all I could do was form linear frontiers, right? But now I have quadratic terms at my disposal. And in fact, with a full polynomial, I can have any polynomial expression. So before, let's suppose that this was my positive class, right? Well, I couldn't represent that. Now I can. A circle, well, it's a quadratic equation. I can implement it using this. Or a parabola, check. Or a hyperbola, check, right? Now I can represent quadratic frontiers. And, remember, this is in hyperspace, right? So, there were all these problems that, the perceptron couldn't do that just because of this, now it can. Okay? And if I go to higher order polynomials, I can represent, higher order curves and so on and so forth. So now instead of those jaggedy nearest neighbor frontiers, I can have very beautiful, smooth frontiers between positive and negative, right? It's much more aesthetically pleasing. Like there's these like Java applets on the web that you can play with that, they're so beautiful they'll bring a tear to your eye. Not ugly like, nearest neighbor or even decision trees. It's very nice. Okay. Of course, in some cases, decision trees and nearest neighbor are still better, but nevertheless. Okay. The main point here is that this trick, the kernel trick, brought us a lot of power. Right? We can now we can now at least represent a lot of things that we couldn't before. And because we have a nice quadratic optimization problem, a lot of the time we are going to be able to learn that in practice, and we will see that starting at 8:13. Okay? All right. Okay.